Hello, friend. Some nights feel wider than they should. The dark stretches longer. Silence holds more weight. Maybe that's just the universe reminding us how small we are, or how much we've yet to see. Tonight we're drifting to the edge of everything we know. Not to the stars you can name, but to the ones you've never heard of. To a place so far that light takes over 4 hours to reach it. To a moon that isn't really a moon at all. Her name is Charon, and she's been waiting in the dark for 4.6 billion years, locked in a dance with a world we barely remember. Before we begin this quiet journey together, I want to say thank you for being here. If you find comfort in these soft-spoken stories about the universe, you might like to gently tap the like button below. It helps others find their way here too. And if you'd like more nights like this where science is whispered, not shouted, you can subscribe and ring the bell. Not for noise, but so the next quiet story can find you again when you need it most. Now, let's drift. Imagine two dancers alone on a stage no one watches. They move in perfect time, never looking away, never drifting apart. One is small and pale, the other smaller still. They've been dancing this way since before the dinosaurs, before the oceans, before Earth had a name. This is Pluto and Charon, and their story begins not with discovery, but with forgetting. For most of human history, we didn't know Pluto existed. And when we finally found it in 1930, we thought it was alone. A frozen exile at the edge of the solar system, spinning in silence, abandoned by the sun. We gave it a name from the underworld Pluto, god of the dead, and we moved on. It was too far, too cold, too dark to matter. But Pluto wasn't alone. It never had been. In 1978, a man named James Christie was studying photographs of Pluto at the U.S. Naval Observatory in Flagstaff, Arizona. The images were grainy, blurred, imperfect, taken with technology that now seems ancient. But Christie noticed something strange. Pluto wasn't round in the pictures. It had a bulge, a wobble, a bump that appeared and disappeared every few days like something was pulling at its edges. At first, scientists thought it was a flaw in the telescope, a smudge on the lens, a trick of the light. But Christie kept looking. He studied plate after plate, image after image, and the bump was always there, always in the same rhythm, always in the same place. He realized what it meant. Pluto wasn't alone. Something was orbiting it, something large enough to distort the image, something we'd been staring at for nearly 50 years without ever seeing. He named it Charon after the ferryman who guides souls across the river Styx in Greek mythology, the one who carries the dead to the underworld. It felt fitting. Charon had been there all along, invisible, carrying Pluto through the dark. But here's what makes Charon different from every other moon we've ever found. She isn't just orbiting Pluto, she's dancing with it. Most moons are small compared to their planets. Earth's moon is about 1/80th the mass of Earth. Mars's moons, Phobos and Deimos, are barely rocks. Even the giant moons of Jupiter, Europa, Ganymede, Callisto, are dwarfed by the planet they orbit. They spin around their worlds like children around a parent held close by gravity. Always smaller, always secondary. But Charon is different. She's not a child, she's a twin. Charon is more than half the size of Pluto. In fact, if you measure their masses, Charon is about 1/8 as heavy as Pluto. That might not sound like much, but in cosmic terms, it's staggering. It means that when Pluto and Charon orbit each other, they don't move like a planet and a moon. They move like two dancers holding hands spinning around a point in space between them. That point is called the barycenter. And in the case of Pluto and Charon, it lies outside Pluto's surface in the empty space between the two worlds. Think about that for a moment. Most planetary systems have a clear center. Earth and the moon orbit a barycenter too, but it's deep inside Earth's core, so it looks like the moon circles us. Jupiter and its moons, same thing. The barycenter is buried so far inside Jupiter that the moons appear to orbit the planet itself. But with Pluto and Charon, the center of their dance is in the void. Neither one is the anchor, neither one is the moon. They're just two bodies holding each other in the dark, refusing to let go. Some scientists don't even call Charon a moon anymore. They call the system a binary planet. Two worlds, not one. Partners, not parent and child. And that changes everything. Because if Charon isn't a moon, then what is she? Where did she come from? Why is she so large, so close, so perfectly matched to Pluto's rhythm? And why in all the billions of years they've been spinning together, have they never once looked away? The answer lies not in observation, but in violence. Not in what we see now, but in what happened long ago when the solar system was still young and wild and full of collisions. Scientists believe Charon wasn't born from Pluto. She was born from what destroyed it. About 4.6 billion years ago, when the planets were still forming, the outer solar system was chaos. Massive chunks of ice and rock hurtled through space, smashing into each other, merging, shattering, reforming. Pluto was there, still soft, still molten, still finding its shape. And then something hit it. Something huge. The impact was catastrophic. A body, perhaps 1/3 the size of Pluto, slammed into it at thousands of miles per hour, releasing energy beyond comprehension. The surface of Pluto exploded. Pieces of its outer layers, ice rock, frozen gases, were blasted into space, forming a ring of debris around the shattered world. But gravity is patient. Slowly, over millions of years, that debris began to clump together. It coalesced, it condensed, and eventually it formed a second body. A body made not from new material, but from Pluto's own flesh and bone. That body was Charon. This is called the giant impact hypothesis. And it's the same theory we use to explain the birth of Earth's moon. Around 4.5 billion years ago, a Mars-sized object called Theia collided with the early Earth, and the debris from that collision eventually formed the moon. It's why the moon's composition is so similar to Earth's outer layers. It's why the moon is unusually large for a satellite. It's why we exist at all, because that collision gave Earth the tilt and rotation that created seasons, climates, life. But here's the difference: Earth's moon is only 1.2% of Earth's mass. Charon is 11.6% of Pluto's mass. The impact that created Charon must have been proportionally far more violent, far more destructive. It wasn't a glancing blow, it was a catastrophe. And yet from that catastrophe, something beautiful emerged. Two worlds bound together forever. A partnership born from destruction. Scientists can simulate this collision using supercomputers. They input the size, speed, and angle of the impact, and they watch what happens. In these simulations, Pluto doesn't just crack, it nearly tears apart. The debris disk spreads wide, glowing with heat, spinning in chaos. But slowly, frame by frame, the disk begins to condense. First into rings, then into clumps, and finally into a single massive moon. The simulations match what we see today. Charon's low density, about 1.7 grams per cubic centimeter, suggests she's made mostly of water ice, with very little rock or metal. That makes sense if she formed from Pluto's outer layers, which were rich in ice, but poor in heavy elements. Pluto's core, where the iron and rock would have been concentrated, stayed intact. Only the surface was lost. So Charon is in a way a piece of Pluto, a fragment, a scar that became a companion. And she's been there ever since, circling the wound she came from, never straying, never leaving, always watching. But there's something else, something even stranger. Charon and Pluto don't just orbit each other, they're locked, tidally locked, completely and perfectly synchronized. What that means is this: Pluto rotates once every 6.4 Earth days. Charon orbits Pluto once every 6.4 Earth days. So, from Pluto's surface, Charon never moves. She hangs in the same spot in the sky forever. And from Charon's surface, Pluto does the same. They always face each other. Always. For billions of years. This isn't unusual for moons. Our moon is tidally locked to Earth, which is why we always see the same side. The face of the moon never changes. But Earth isn't locked to the moon. We still spin freely day and night while the moon watches from above. Pluto and Charon are different. They're both locked, mutually. If you stood on one side of Pluto, Charon would be frozen in your sky, never rising, never setting. If you stood on the other side of Pluto, you'd never see Charon at all. She'd be hidden forever, just beyond the horizon, like a secret you were never meant to know. And the same is true from Charon. Half of Charon always sees Pluto. Half never does. It's the most perfect partnership in the solar system, a bond so complete that neither world can look away. But how does this happen? How do two worlds become so perfectly synchronized? The answer is tidal forces. The same forces that pull our oceans into tides that stretch and squeeze Europa's icy shell that will one day drag our moon farther from Earth. Tidal forces are caused by gravity, not the gravity that holds things together, but the gravity that pulls them apart. When two objects orbit each other, the side closest to the partner feels stronger gravity than the side farthest away. This creates a bulge. Over time, this bulge acts like a brake, slowing the rotation of both bodies. Eventually, the rotation slows so much that one side always faces the partner. That's tidal locking. For most moons, only the moon gets locked. The planet is too massive, too stubborn to slow down. But Pluto and Charon are so close in size, so perfectly matched, that they locked each other. It took millions of years, maybe tens of millions. But eventually, the friction, the tides, the endless pull of gravity brought them into perfect sync. And now, they're frozen there, forever facing, forever watching, forever together. It's rare. In our entire solar system, Pluto and Charon are the only confirmed example of mutual tidal locking. There are binary asteroids that might be locked, and some scientists think Neptune's moon Triton might one day lock with Neptune. But right now, Pluto and Charon stand alone, a partnership so deep that even time can't break it. And yet, for all their closeness, we barely know them. For decades after Charon's discovery, we only had blurry images, pixels, guesses. We knew she was there, and we knew she was large, but we didn't know what she looked like. We didn't know if she had mountains, craters, ice. We didn't know if she was smooth or scarred, bright or dark. All we knew was that she was there, waiting, dancing, holding Pluto in the dark. It would take 37 years and a spacecraft traveling faster than any bullet to finally see her face. But we'll come to that. For now, just imagine them. Two frozen worlds spinning together at the edge of the solar system, so far from the sun that it looks like just another star. They don't warm each other. They don't light each other. They're both cold, both dark, both silent. But they're not alone, and maybe that's enough. We'll return to them soon as we drift deeper into Charon's story. Into the surface she hides the secret she carries and the mission that finally brought her into the light. Sometimes the most important things are the ones we almost miss. In 1978, an astronomer named James Christie was staring at photographs that didn't make sense. Pluto looked wrong, blurred, distorted, like something was pulling at its edges, stretching it into shapes it shouldn't have. Most people would have blamed the telescope. Christie looked closer. What he found wasn't a flaw, it was a moon. A moon we'd been photographing for nearly 50 years without ever seeing. And the story of how he found it teaches us something strange about discovery itself, that sometimes we only find what we're ready to see. The year was 1978, but the technology was from another era. Astronomers didn't have digital cameras or computer-enhanced images. They used photographic plates, large sheets of glass coated with light-sensitive emulsion, exposed through telescopes for hours at a time. The longer the exposure, the more light you could gather. The more light, the better chance you had of seeing something faint and far away. Pluto was both. At its closest, it's still 2.7 billion miles from Earth. At its farthest, over 4.6 billion. A frozen world smaller than our moon, reflecting almost no sunlight, drifting through a darkness so complete that the sun looks like just another bright star, To photograph Pluto, astronomers had to expose their plates for hours tracking the telescope, as Earth rotated, keeping Pluto centered in the frame. But even with perfect tracking, even with the best equipment, the images were never sharp. Pluto appeared as a small, fuzzy blob, a dim smudge against the black, nothing more. That's what James Christie expected to see when he examined a new set of plates taken at the U.S. Naval Observatory in Flagstaff, Arizona. The observatory had been photographing Pluto as part of a routine program to refine its orbit to measure its position with greater accuracy. Christie's job was to analyze the images to measure Pluto's location, down to fractions of an arc second. But when he looked at the plates, something was wrong. Pluto wasn't round. It had a bulge, a bump protruding from one side, like a growth like a tumor, like something that shouldn't be there. At first, Christie thought the telescope had slipped. Maybe the tracking mechanism had malfunctioned, smearing Pluto's image across the plate. It happens. Equipment fails, machines drift. But when he checked the background stars, they were perfectly round, perfectly sharp. The telescope hadn't moved. The problem was Pluto itself. Or rather, it was something near Pluto. Christie pulled older plates from the archives, images taken weeks, months, years earlier. And the bump was there too. Not always in the same place, sometimes it extended to the north, sometimes to the south. But always there, always visible, always in rhythm. He measured the timing. The bump appeared and disappeared in a cycle. Every 6,387 days, it would shift position, rotating around Pluto like a clock hand. That was too regular to be a mistake, too consistent to be noise. Christie realized what he was looking at. It wasn't a flaw in the image. It wasn't a distortion. It was a moon. A moon so close to Pluto that the two overlapped in the photograph, blurring into a single elongated shape. The bump wasn't Pluto. It was Charon. But here's what makes this discovery so remarkable. Charon had been in those photographs the entire time. Since Pluto's discovery in 1930, astronomers had taken thousands of images. Every one of them showed the same bump, the same wobble, the same distortion. But no one noticed. No one looked closely enough. No one asked the right question. Why? Because we see what we expect to see. And in 1930, no one expected Pluto to have a moon. It was too far, too small, too insignificant. Moons were things that orbited real planets, Jupiter, Saturn, maybe Mars. But Pluto was barely a planet itself. Why would it have a companion? So, for nearly 50 years, Charon hid in plain sight. Invisible, not because she was hidden, but because we weren't looking. Christie's discovery changed everything. But it wasn't immediate. It wasn't obvious. When he first announced his findings, many astronomers were skeptical. The images were too blurry, the evidence too indirect. Maybe it was an optical illusion. Maybe Pluto was just shaped strangely elongated, rotating in a way that created the appearance of a bulge. But Christie was persistent. He predicted that if Charon was real, then Pluto and Charon would eventually eclipse each other as seen from Earth. Their orbits were tilted, so for most of the time, we see them from the side, never crossing. But every 124 years, their orbital plane aligns with our line of sight, and they begin passing in front of each other. Christie calculated that this alignment was about to happen. Starting in 1985, Pluto and Charon would begin a series of mutual eclipses events, where one body passes in front of the other, dimming the combined light we see. If Charon existed, the eclipses would follow a precise pattern. If she didn't, nothing would happen. The eclipses began right on schedule. In 1985, astronomers watched as Pluto's brightness dipped, then recovered, then dipped again, like clockwork. Each eclipse lasted hours, occurring every 6,387 days, exactly as Christie predicted. The pattern was unmistakable. Charon was real. And more than that, the eclipses revealed something extraordinary. By measuring how much light disappeared during each eclipse, scientists could calculate Charon's size. And she was huge. far larger than anyone expected. About 750 miles in diameter compared to Pluto's 1,477 miles, more than half Pluto's size. A moon so massive that calling her a moon felt almost misleading. This was unprecedented. No other planet in the solar system had a moon so proportionally large. Earth's moon is impressive, but it's only about 1/4 Earth's diameter. Mars's moons are tiny. Phobos is just 14 miles across Deimos, only 7.8. Even Jupiter's massive moons, Ganymede, Callisto, Io, Europa, are dwarfed by Jupiter itself. But Charon was nearly half of Pluto, a twin, not a satellite. The eclipses continued for 5 years, from 1985 to 1990. Each one provided more data, more measurements, more precision. By the end, scientists had mapped the system in detail. They knew Charon's size, her orbit, her mass. They knew she was made mostly of water ice with very little rock. They knew she was tidally locked to Pluto, always showing the same face. They knew the system was ancient, stable, unchanging, but they still didn't know what she looked like. Because here's the frustrating truth. Even after Charon was discovered, even after the eclipses, even with the best telescopes on Earth, we still couldn't see her clearly. She was too small, too far, too dim. The Hubble Space Telescope, launched in 1990, could just barely separate Pluto and Charon into two distinct points of light. But details, surface features, craters, mountains, ice, impossible. For decades, Charon remained a ghost, a presence we could measure but not see, a moon we knew existed but couldn't truly know. And that leads to a deeper question, one that haunts all of astronomy: how much are we still missing? Think about it. Charon was right there in our photographs for half a century. Thousands of images, hundreds of astronomers, and no one saw her. Not because the technology was inadequate, the images were good enough, as Christie proved, but because no one was looking. No one asked the question, how many other discoveries are hiding in old data, waiting for someone to notice? How many moons, planets, galaxies, phenomena are sitting in archives right now, overlooked, forgotten, invisible? Not because they're hidden, but because we don't expect them. Scientists call this the file drawer problem. Data that doesn't show what we expect tends to get ignored, filed away, forgotten. We look for patterns we recognize. We search for answers we've already imagined. And in doing so, we miss the answers we couldn't have predicted. Charon teaches us humility. She reminds us that discovery isn't always about better tools or bigger telescopes. Sometimes it's just about looking at the same thing differently. About noticing the wobble, the bulge, the imperfection that everyone else dismissed. Christie didn't have better equipment than his predecessors. He just paid attention. He trusted the anomaly. He asked why Pluto looked wrong instead of assuming the images were flawed. And because of that, he found a world. But discovery is only the beginning. Knowing Charon existed didn't tell us who she was. It didn't reveal her surface, her history, her secrets. For that, we needed to go there. To cross the solar system, to travel for nearly a decade, to fly past her at thousands of miles per hour, with cameras ready, hoping to capture a glimpse before she vanished back into the dark. That mission would take 37 more years to arrive. And when it did, it would show us something no one expected. A moon that wasn't dead. A moon that wasn't quiet. A moon that carried scars, mysteries, and questions we still don't know how to answer. But finding her was the first step. Seeing the invisible. Trusting the wobble. Believing that even in the blur, even in the imperfection, something real was waiting to be known. And so, Charon emerged from the darkness. Not all at once, not clearly, but slowly, patiently, the way all true discoveries happen, one careful observation at a time, one question asked when everyone else had moved on. She'd been there all along. We just needed someone to see. The eclipses ended in 1990, and Charon faded back into obscurity. 2 points of light in a telescope, a statistic in a database, a moon most people had never heard of, orbiting a planet most people had forgotten. But scientists didn't forget, because Charon wasn't just a moon. She was a puzzle, an anomaly, a clue to something deeper, to how planets form, how collisions shape worlds, how gravity binds things together in ways we're still learning to understand. And that puzzle would take us to the edge of the solar system, into the cold and the dark, chasing answers we didn't even know we needed. Picture 2 ice skaters' hands clasped spinning in the center of an empty rink. They're not circling each other, they're circling a point between them, a place neither one occupies. Faster and faster, they spin perfectly balanced, perfectly matched. If one lets go, both will fly apart into the dark. This is Pluto and Charon, not a planet and its moon, not a parent and child. Something rarer, something physics calls a binary system, but what might be better described as a cosmic partnership. And the mechanics of their dance reveal something extraordinary about gravity balance and what it means to orbit. Most of us learn about orbits the same way. The Earth goes around the Sun. The Moon goes around the Earth. Jupiter's moons go around Jupiter. It's simple. It makes sense. One object is large and stationary. The other is small and moves. But that's not quite true. In reality, nothing in space is truly stationary. When the Moon orbits Earth, Earth also moves. Not much, just a tiny wobble, but it moves. The same is true for Jupiter and its moons, for Saturn, and its rings for every planet and satellite in the universe. They all orbit a shared center of mass, a point called the barycenter. Think of it like a seesaw. If you put a child on one side and an adult on the other, the pivot point isn't in the middle, it's much closer to the adult, because the adult is heavier. The child moves a lot. The adult barely moves at all, but both are moving around the same point. In most planetary systems, the barycenter is buried deep inside the planet itself, because the planet is so much more massive than its moons. Earth is 81 times more massive than the moon, so the barycenter of the Earth-Moon system is about 1,000 miles below Earth's surface, deep inside the mantle nowhere near the moon. From our perspective, it looks like the moon orbits us. And in a way, it does. But technically, we're both orbiting an invisible point beneath our feet. Jupiter's barycenter with its moons is the same. Even with massive moons like Ganymede and Callisto, Jupiter is so enormous that the barycenter stays comfortably inside its core. Jupiter wobbles slightly as its moons orbit, but the wobble is so small, it's almost irrelevant. Jupiter is the anchor, the moons are the dancers, but Pluto and Charon, they're different. Charon is 11.6% the mass of Pluto. That doesn't sound like much, but in cosmic terms, it's staggering. To put it in perspective, if Charon were orbiting Earth instead of Pluto, she'd be 9 times more massive than our moon. If she were orbiting Mars, she'd be 1,000 times more massive than Phobos. She's not a small satellite tagging along for the ride. She's a partner. And because of that, the barycenter of the Pluto-Charon system doesn't sit inside Pluto. It sits in the space between them, about 580 miles above Pluto's surface. Neither Pluto nor Charon orbits the other. They both orbit this empty point, this invisible fulcrum spinning around it every 6.387 days in perfect synchrony. This makes them a binary planet system, the only confirmed one in our solar system. Some scientists argue that Earth and the Moon should also be considered a binary system, since our Moon is so large relative to Earth. But the International Astronomical Union disagrees. The rule they use is simple. If the barycenter is outside the primary body, it's a binary system. If it's inside, it's a planet-moon system. By that definition, Earth-Moon is still a planet and satellite. Pluto-Charon is something else entirely. But does the label matter? Does it change what they are? Maybe not. But it changes how we think about them. Because when you stop seeing Charon as Pluto's moon and start seeing them as partners, the questions shift. You stop asking, why does Pluto have such a large moon? And start asking, why are these two worlds bound together? You stop thinking about capture and start thinking about collision. You stop imagining one object holding another and start imagining two objects holding each other. And that's when the story gets deeper. Let's talk about orbital mechanics for a moment. When two objects orbit a shared barycenter, they follow precise mathematical rules. The more massive object moves slowly in a small circle. The less massive object moves quickly in a larger circle. But both take the same amount of time to complete one orbit because they're locked together by gravity. Pluto takes 6.387 days to circle the barycenter. Charon takes 6.387 days. Pluto travels in a circle with a radius of about 1,370 miles. Charon travels in a circle with a radius of about 1,260 miles. Pluto moves at about 50 miles per hour relative to the barycenter. Charon moves at about 450 miles per hour. Different speeds, different distances, but the same rhythm. This is called synchronous rotation, and it's rare. Not impossible binary asteroids sometimes achieve it. And some scientists believe Neptune's moon Triton might eventually lock into a binary dance with Neptune billions of years from now. But among the planets and moons we can study up close, Pluto and Charon are unique. Compare them to other systems. Earth and the moon are not in synchronous rotation. The moon is tidally locked to Earth. Yes, it always shows us the same face. But Earth is not locked to the moon. We spin freely, completing one rotation every 24 hours, while the moon takes 27.3 days to orbit. From the moon's surface, Earth rises and sets in the sky. From Earth, the moon drifts across our view, waxing and waning, appearing and disappearing. But Pluto and Charon never see each other move. From Pluto's surface, Charon hangs motionless in the sky, fixed in place like a painting. From Charon, Pluto does the same. If you stood on one side of Pluto, Charon would be visible forever. If you stood on the other side, you'd never see her at all. She'd be hidden beyond the curve of the horizon, permanently out of sight, like a partner you know exists but can never touch. Why does this happen? How do two worlds become so perfectly balanced? The answer is time. Enormous stretches of time combined with tidal forces. When Charon first formed, whether from a collision or some other process we'll explore later, she was probably much closer to Pluto than she is now. And her rotation was likely chaotic, tumbling end over end, not synchronized at all. Pluto too was spinning freely, completing a day in just a few hours. But gravity doesn't just pull objects together, it stretches them. The side of Pluto facing Charon experiences slightly stronger gravity than the side facing away. This creates a tidal bulge, a stretching of Pluto's shape pulling it toward Charon, like dough being pulled apart. That bulge acts like a brake. As Pluto spins, the bulge tries to stay aligned with Charon, but Pluto's rotation drags it forward. This creates friction, which dissipates energy as heat. Over millions of years, that friction slows Pluto's rotation bit by bit, until finally Pluto stops spinning faster than it orbits. The bulge locks into place, always facing Charon. Pluto is now tidally locked. The same process happens to Charon, but faster because Charon is smaller, and Pluto's tidal forces on her are stronger. Charon locks to Pluto first. Then over a longer time scale, Pluto locks to Charon. Once both are locked, the system becomes stable. Neither one can drift away because their mutual gravity holds them in place. Neither one can spin faster because the tidal forces have already slowed them to equilibrium. They're frozen in a dance that will last as long as the solar system itself. Scientists estimate this locking process took between 10 and 100 million years. That sounds like a long time, but in cosmic terms, it's a blink. Pluto and Charon have been locked together for over 4 billion years. The dance is far older than the locking. The bond predates the balance. And here's what's strange: mutual tidal locking is supposed to be temporary. Over billions of years, tidal forces should push Charon farther from Pluto, increasing her orbit, slowing the system down. Eventually, Charon should drift so far that the lock breaks, and both worlds start spinning freely again. But that hasn't happened. Pluto and Charon are still locked, still close, still perfectly synchronized. Why one possibility is that Charon is moving away, but so slowly that we can't measure it yet. The rate of drift might be just millimeters per year, too small to detect with current technology. In another few billion years, Charon might be twice as far from Pluto as she is now, and the system might look completely different. Another possibility is that something else is stabilizing the system. Perhaps Pluto's other moons, Styx, Nix, Kerberos, Hydra, play a role exerting gravitational influences that keep Charon in place. Or perhaps the system reached a perfect equilibrium, a balance point, where tidal forces no longer push Charon away because the energy has already been fully dissipated. We don't know. And that's part of what makes Pluto and Charon so fascinating. They shouldn't exist the way they do. They shouldn't be so perfectly matched, so tightly bound, so completely synchronized. And yet they are. Some scientists call them the strangest pair in the solar system. Not because they're alien or mysterious, but because they're so perfectly ordinary in their weirdness. They follow all the rules of orbital mechanics. They obey gravity tidal forces, conservation of angular momentum. There's nothing supernatural about them. They're just rare. A fluke of formation, a coincidence of size and distance and timing that aligned in exactly the right way to create something no other planet has. And that rarity makes them precious. Because in studying Pluto and Charon, we're not just learning about two distant worlds. We're learning about what's possible, about how planets can form, how collisions can create instead of destroy, how gravity can bind things together in ways we never imagined. There are other binary systems in the universe. Binary stars where two suns orbit each other. Binary asteroids where two rocks tumble together through the asteroid belt. Scientists even speculate that some exoplanets might have binary companions, double worlds orbiting distant stars, locked in dances we'll never see up close. But Pluto and Charon are ours. Close enough to visit, close enough to photograph, close enough to study, to measure, to understand. And what we've learned from them is this partnership is possible even in the coldest, darkest, loneliest corners of the solar system. Two worlds holding each other, refusing to let go. Not because they have to, not because they're forced, but because the physics of their existence, the gravity of their shared history, binds them together in a way neither can escape. Some might call that captivity. But maybe it's something else. Maybe it's balance. Maybe it's trust. Maybe it's the universe showing us that even in a void where nothing should stay together, some things do. And they dance, quietly, endlessly, perfectly. Not for us, not for anyone, just for each other. But the question remains, how did they become partners in the first place? What force brought them together? What event locked them into this eternal waltz? The answer lies not in the present, but in the past. In a moment of violence so immense it reshaped both worlds forever. There's a moment in every creation story where something breaks, a shell cracks, a star explodes, a world shatters into pieces that shouldn't fit back together, but somehow do. And sometimes from that breaking, something new emerges, not despite the violence, but because of it. 4.5 billion years ago, something hit Pluto, something enormous. And from that collision, from that catastrophic breaking, Charon was born. Not gently, not slowly, but in a flash of heat and destruction so complete that it melted worlds. Picture the early solar system, not the orderly, predictable clockwork we see today, but chaos. A swarm of planetesimals, chunks of rock and ice ranging from pebbles to small planets hurtling through space, colliding, merging, shattering. The sun is young, blazing with violent energy. The inner planets are still molten, still soft, still finding their shapes. And out at the edge in the cold and the dark, Pluto is forming. She's not alone. The Kuiper Belt. The vast region beyond Neptune is crowded with objects. Thousands of them, millions. Bodies made of ice and rock leftovers from the solar system's formation, drifting in orbits that cross and intersect and collide. Pluto is one of the largest, but she's not special. Not yet. She's just another frozen world growing slowly as smaller objects crash into her, adding mass, adding heat, adding gravity. And then one day, something much larger appears. An object, perhaps 1/3 the size of Pluto, drifting toward her on a collision course. It's not intentional. There's no malice, no purpose. It's just gravity pulling two bodies toward each other until they meet. The impact happens at thousands of miles per hour, not head-on, but at an angle, a glancing blow that's somehow worse than a direct collision because it doesn't just destroy, it rips. The impactor strikes Pluto's outer layers, and the force is unimaginable. The energy released is equivalent to billions of nuclear bombs detonating simultaneously. Pluto's surface doesn't just crack, it explodes. Rock and ice are blasted into space. Some escape entirely, flung out into the Kuiper Belt, never to return. But most of it stays held by Pluto's gravity, forming a vast disk of debris orbiting the shattered world. For a moment, Pluto has rings. Not elegant ordered rings like Saturn's, but a chaotic swirl of molten rock, vaporized ice, and shattered fragments glowing with heat. Pluto herself is wounded. Her outer layers are gone, peeled away like skin. Her core, denser, rockier, heavier, remains intact but exposed. The heat from the impact melts what's left of her surface, turning her into a ball of slush, a world caught between solid and liquid, too hot to freeze, too cold to stay molten. And in the disk above her, something is happening. The debris is beginning to condense. This is how moons are born from collisions. Not instantly, but gradually, over thousands or millions of years. The debris disk orbits Pluto, and as it does, the pieces inside it begin to collide. Not violently this time, but gently sticky collisions between ice and ice, rock and rock. The pieces stick together. They clump. They grow. At first, there are hundreds of small clumps, each one competing for material, each one growing at the expense of its neighbors. But over time, one clump grows faster than the others. It has more mass, more gravity, more pull. It begins to sweep up the debris around it, absorbing everything in its path, growing larger and larger. That clump becomes Charon. Scientists call this the giant impact hypothesis. And it's the leading explanation not just for Charon's formation, but for the moons as well. About 4.5 billion years ago, a Mars-sized object named Theia collided with the early Earth. The impact was so violent it nearly destroyed both worlds. Debris from Earth's outer layers was blasted into orbit, and over time, that debris coalesced into the moon. It's why the moon's composition is so similar to Earth's crust, because the moon is made from Earth's crust, torn away, and reformed. But there are differences between the Earth-Moon system and the Pluto-Charon system, important ones. First, the scale of the collision. Theia was about 10% the mass of Earth. The object that hit Pluto was likely 30 to 40% of Pluto's mass. Proportionally, the Pluto impact was far more catastrophic. If an object that size hit Earth today, it wouldn't just create a moon. It might destroy the planet entirely, breaking it into fragments that would never reassemble. Second, the composition. Earth's moon is rocky dense, made mostly of silicates and metals. Charon is icy light made mostly of water ice with very little rock. That tells us the collision happened in a colder part of the solar system, where ice was the dominant material, not rock. It also tells us that Charon formed from Pluto's outer layers, which were rich in ice, while Pluto's core, where the heavier elements were concentrated, stayed intact. Third, the timing. The Earth-Moon collision happened early when Earth was still molten, still forming. The energy from the impact contributed to Earth's internal heat, helping to power plate tectonics and volcanism for billions of years. But the Pluto-Chiron collision may have happened later, after Pluto had already partially cooled. The impact reheated Pluto's surface, melting it again, but the core remained solid, stable, unchanged. And fourth, the outcome. The moon is about 1.2% the mass of Earth. Charon is 11.6% the mass of Pluto. That's a staggering difference. It means the Pluto collision didn't just create a moon, it created a partner. A companion so large that the system became binary with both worlds locked in orbit around a point neither one controls. How do we know this? How can scientists be so confident about an event that happened 4.6 billion years ago, long before any witness, any observer, any record? The answer is computer simulations. Using supercomputers, researchers can model the collision in extraordinary detail. They input the size, speed, angle, and composition of the impactor, and they watch what happens. The simulation runs forward in time, calculating the motion of millions of particles as they collide, merge, and condense. In 2005, a team led by planetary scientist Robin Canup ran such a simulation at the Southwest Research Institute in Colorado. They tested dozens of scenarios varying the size and speed of the impactor, looking for one that matched what we observe today, Charon's mass orbit and composition. They found it. In their simulation, an object about 1,000 kilometers in diameter struck Pluto at a speed of roughly 1 kilometer per second, fast, but not catastrophically fast. The impact was oblique, hitting at an angle of about 30 degrees. The result was a debris disk that orbited Pluto for several thousand years before condensing into a single large moon, Charon. The simulation explained everything: Charon's size, her low density, her circular orbit. It even explained why Pluto and Charon are tidally locked, because tidal forces act faster on moons that form close to their parent bodies. And Charon formed very close to Pluto, well inside the distance she orbits today. But simulations aren't proof. They're just models, educated guesses based on physics and math. Is there any other evidence that Charon was born from a collision? Yes. Her density. Charon's density is about 1.7 grams per cubic centimeter. That's lower than Pluto's density, which is about 1.86 grams per cubic centimeter. That difference is small but significant. It tells us Charon has less rock and metal than Pluto and more ice. That's exactly what you'd expect if Charon formed from Pluto's outer layers, which were ice-rich, while Pluto's core, where the rock and metal are concentrated, stayed behind. If Charon had formed separately far from Pluto and been captured later, her density would likely be different. She might be rockier or icier depending on where she formed. But instead, her density matches what we'd expect from a collision, a fragment of Pluto's mantle reformed into a new world. There's also the orbital evidence. Charon's orbit is nearly circular with very low eccentricity. That's unusual for a captured moon. When moons are captured, they usually have elliptical orbits stretched, elongated, unstable. But Charon's orbit is calm, smooth, perfectly circular. That's what you'd expect from a moon that formed in place from a debris disk, rather than one that was pulled in from elsewhere. And then there's the tidal locking. Captured moons can become tidally locked, but it takes a very long time. Charon and Pluto are both tidally locked mutually, which suggests they've been close together for most of their history. That fits the collision model, where Charon formed nearby and never drifted far. But not everyone agrees with the giant impact hypothesis. Some scientists have proposed alternative explanations. Maybe Charon formed separately in the Kuiper Belt and was captured by Pluto's gravity during a close encounter. Maybe Pluto and Charon formed together as a binary system from the same cloud of gas and dust. Maybe there was a collision, but it was much gentler than the simulations suggest, a merger rather than an impact. Two bodies drifting together and sticking like drops of water. These alternatives are possible, but they're harder to reconcile with the evidence. Capture scenarios struggle to explain the mutual tidal locking. Co-formation scenarios struggle to explain the size difference and density mismatch. Gentle mergers struggle to explain the heat required to differentiate both bodies. The giant impact hypothesis isn't perfect, but it fits better than anything else we've thought of. And there's something almost poetic about it. The idea that Charon is not a stranger, but a piece of Pluto. A fragment torn away, reformed, returned. Not an invader, but family. Not a capture, but a reunion. Collisions are usually seen as destructive. We think of asteroids wiping out dinosaurs, comets, scarring moons, planets shattering into dust. But the Pluto-Charon collision wasn't just destruction. It was creation. It was transformation. It was the universe taking something broken and making it whole again in a different form. And that raises a deeper question: how much of what we see, how much of the beauty, the order, the structure of the solar system was born from violence? How many moons are scars? How many planets are survivors? The answer scientists believe is most of them. The solar system we live in today is not pristine. It's not untouched. It's a battlefield shaped by billions of years of collisions, impacts, catastrophes. Earth exists because of collisions. The moon exists because of collisions. Mars lost its atmosphere because of collisions. Jupiter's moons, Saturn's rings. The asteroid belt itself, all shaped by impacts, by breaking by chaos, made ordered through time. Charon is not an exception. She's the rule. She's what happens when the universe builds something new from the wreckage of the old. And she's still there orbiting Pluto, forever facing the world she came from. A companion born from violence, held close by gravity, locked in a dance that will outlast stars. But birth is only the beginning. What Charon became, what her surface looks like, what her geology reveals, what secrets she carries would remain hidden for billions of years, until a spacecraft the size of a piano flew past her at 30,000 miles per hour. And finally, we saw her face. For most of human history, Charon was invisible. Then she was a dot, then a blur. Then on July 14th, 2015, she became real. Not an abstraction, not a calculation, but a place. A world with geography, with texture, with a face no one had ever seen before. And what that face revealed was stranger than anyone expected. The images came back slowly, pixel by pixel, line by line, transmitted across 3 billion miles of empty space at the speed of light. And when scientists finally assembled them into a complete picture, they saw something that shouldn't exist. A moon that was supposed to be dead, cratered, unremarkable, but instead looked like it had been carved, stretched, painted by forces no one could fully explain. On July 14, 2015, NASA's New Horizons spacecraft flew past Pluto and Charon at a speed of 30,800 miles per hour. It had traveled for 9.5 years to get there, crossing the entire solar system, and it had just hours to observe. Hours to photograph, to measure, to record everything it could, before disappearing into the Kuiper Belt, never to return. The mission was a gamble. New Horizons couldn't orbit Pluto. It was moving too fast and carrying too little fuel. It could only fly past, taking pictures as it went, storing the data on its internal memory, and then slowly over the next 16 months, transmitting it back to Earth. One mistake, one malfunction, one missed photograph, and it would be lost forever. But the spacecraft didn't fail, and the images it captured changed everything we thought we knew about the outer solar system. Charon's surface, as seen by New Horizons, is a study in contrasts. The southern hemisphere is ancient, heavily cratered, scarred by billions of years of impacts. But the northern hemisphere is different, smooth, young, geologically active, or at least it was relatively recently. And cutting across the equator, running for hundreds of miles, is a system of canyons so deep and vast that they dwarf anything on Earth. Let's start with the canyons. The largest is called Serenity Chasma, named after the fictional spaceship in the TV show Firefly. It's not a single canyon, but a network of them, fractures in Charon's crust that run for over 1,000 miles, cutting across her face like scars. In places, the canyon walls drop nearly 5 miles straight down, deeper than the Grand Canyon, deeper than the Mariana Trench. Some sections are over 4 miles deep and 45 miles wide. These aren't impact craters. They're tectonic features created by the stretching and cracking of Charon's crust. But what could cause such enormous fractures on a moon that's supposed to be geologically dead? The answer scientists believe is freezing. When Charon first formed, she was warm. The heat from the collision that created her, combined with the decay of radioactive elements in her interior, kept her partially molten for millions of years. Beneath her icy crust, there was likely a subsurface ocean, a layer of liquid water, miles deep, insulated from the cold of space by the thick ice above. But over time, Charon cooled. Her radioactive elements decayed, releasing less heat. Her surface radiated warmth into space, losing energy. And eventually, the ocean began to freeze. Not all at once, but from the outside in, like a pond freezing in winter. Here's the critical part: water expands when it freezes. Ice takes up about 9% more volume than liquid water. So, as Charon's ocean froze, it expanded, pushing outward against the crust. The crust, already brittle from the cold, couldn't handle the pressure. It cracked. It split. It tore open, forming the massive canyon systems we see today. This process is called cryovolcanism, though it's not quite the same as regular volcanism. Instead of molten rock erupting from below, it's liquid water or slushy mixtures of water and ammonia forced through cracks in the ice. On Earth, volcanoes create mountains. On Charon, they create canyons. But Serenity Chasma isn't the only mystery. There's also the mountain. Rising from Charon's southern plains is a solitary peak officially named Kubrick Mons, but informally called the Mountain in the Moat because it sits in the center of a depression like an island in a crater. The mountain is about 2.5 miles tall, roughly the height of Mount Etna in Italy, and it appears to be made of water ice. Water ice mountains shouldn't be possible. Ice is soft, weak, especially at the cold temperatures of Charon's surface, where it's around 380 degrees Fahrenheit. At those temperatures, water ice behaves like rock on Earth, hard, rigid, brittle. But it's still not strong enough to support mountains miles high. On Earth, mountains are made of rock, held up by the strength of silicate minerals. On Charon, the only material available is ice. So, how does Kubrick Mons stand? One possibility is that the mountain isn't pure water ice. It might contain other materials, ammonia, methane, or rocky debris that strengthen it, giving it the rigidity needed to support its own weight. Another possibility is that the mountain is relatively young, formed recently enough that it hasn't had time to collapse. Or perhaps it's being held up by some internal structure, a pocket of denser material beneath the surface that acts as a foundation. We don't know, and that's what makes it intriguing. Kubrick Mons is a reminder that even on a moon as small and cold as Charon, geology can still surprise us. But the strangest feature on Charon's surface isn't a canyon or a mountain. It's a color. At Charon's North Pole, covering an area roughly the size of New Mexico, is a dark reddish region unlike anything else on the moon. Scientists informally named it Mordor Macula, after the dark land in The Lord of the Rings. It's not a shadow. It's not a crater. It's a stain, a discoloration, a patch of material that absorbs light instead of reflecting it. What is it? The answer scientists believe is tholins. Tholins are complex organic molecules formed when ultraviolet light or cosmic rays hit simpler compounds like methane and nitrogen. They're reddish-brown, sticky, and remarkably stable. They've been found on Titan, Saturn's largest moon, where they create the thick orange haze in the atmosphere. They've been found on comets, asteroids, and even on Mars. But Charon doesn't have an atmosphere. She doesn't have methane oceans or nitrogen lakes. So, where are the tholins coming from? The answer is Pluto. Pluto has an atmosphere, thin, tenuous, but real. It's made mostly of nitrogen with traces of methane and carbon monoxide. And that atmosphere is escaping. Pluto's gravity is weak, so gas molecules at the top of the atmosphere can reach escape velocity and drift away into space. Most of them are lost forever, but some of them are captured by Charon's gravity and fall onto her surface. Over millions of years, this process has painted Charon's North Pole red. The methane molecules freeze onto the ice, and then ultraviolet light from the distant sun breaks them apart, creating tholins. The tholins accumulate layer by layer, building up a dark organic coating that absorbs sunlight and warms slightly just enough to stay sticky, just enough to trap more material. Why only the North Pole? Because of Charon's orientation. Charon is tidally locked to Pluto, but she's not locked to the sun. She rotates slowly, and her poles experience long seasons, decades of sunlight followed by decades of darkness. The North Pole happens to be oriented in a way that makes it a cold trap, a place where escaping gases from Pluto are more likely to freeze and stay frozen. In a way, Pluto is painting Charon, slowly, patiently, molecule by molecule, a parent leaving a mark on a child, or a partner sharing something breath-warmth memory that changes the other forever. It's a strange intimacy. Charon's face is stained with Pluto's atmosphere. She carries pieces of him frozen onto her skin, visible from space. And Pluto, in turn, is shaped by Charon's gravity, locked into a rhythm he can't escape. They don't just orbit each other, they shape each other, they leave marks. Compare this to other moons. Europa, one of Jupiter's moons, has a surface that's geologically active, constantly resurfacing, erasing old craters with new ice. Enceladus, one of Saturn's moons, shoots geysers of water vapor into space, creating a faint ring around Saturn. Titan has rivers, lakes, weather a full hydrological cycle, but made of methane instead of water. Charon has none of that. She's not active anymore. Her ocean, if it existed, is frozen solid. Her volcanoes, if they ever erupted, have gone silent. Her atmosphere, if she ever had one, has long since escaped into space. She's a relic, a fossil, a moon that stopped changing billions of years ago, and now just waits cold and still in the dark. And yet, she's not boring. Because geology doesn't have to be active to be beautiful. Charon's surface is a record, a history book written in ice and shadow, preserved perfectly because nothing is there to erase it. Every crater is a timestamp. Every canyon is a memory. Every stain is a story. When scientists first saw Mordor macula, they thought it might be a recent impact, a fresh wound that exposed darker material beneath the surface. But the Tholin's theory fit better. It explained the color, the location, the chemistry. And it revealed something profound, that even in the coldest, most isolated places in the solar system, chemistry still happens. Molecules still react. Change, however slow, is still possible. But there's one more feature worth mentioning. A crater near Charon's equator, informally named Organa Crater, after Princess Leia Organa from Star Wars. It's not the largest crater on Charon. That honor goes to an unnamed basin in the southern hemisphere, over 180 miles wide. But it's one of the freshest. Its walls are sharp, its ejecta blanket still visible, rays of bright material spreading out like spokes on a wheel. This crater is young, perhaps only a few 100 million years old, maybe less. It's a reminder that even now, even after 4.6 billion years, the solar system is not finished. Impacts still happen, rocks still collide. The slow grinding chaos of gravity and motion continues shaping worlds in ways both violent and subtle. And here's something to think about. If you stood on Charon's surface at the edge of Serenity Chasma, what would you see? The canyon walls dropping into shadow, so deep the bottom is invisible. The ice beneath your feet gray and ancient, harder than steel at these temperatures. And above you, hanging motionless in the sky, never rising, never setting, Pluto. Pluto would fill your view, not as a disk, not as a dot, but as a world close, massive, textured. You'd see its heart-shaped glacier, Sputnik, Planitia, gleaming faintly in the sunlight. You'd see its dark equatorial band, its nitrogen ice plains, its methane mountains. And you'd know that from Pluto's surface, someone standing there would see you too. Charon frozen in their sky, watching always. Two worlds facing each other across a void, painted by each other's presence. Neither one alone, neither one whole, but together, complete. The images from New Horizons are still being analyzed. Scientists are still finding new features, new details, new questions hidden in the data. Charon is not a simple world. She's a puzzle, and every answer raises more questions. Why did her ocean freeze so quickly? What caused the specific pattern of her canyon system? How old is Mordor macula really? Could there still be liquid water deep below her surface, insulated from the cold, waiting to be discovered? We don't know, and we may never know. New Horizons flew past Charon once, and it's never coming back. No other mission to Pluto or Charon is planned, not in this decade, maybe not in this lifetime. Charon has been seen, but she has not been understood. And now, she's fading back into the dark, a memory preserved in data, a face glimpsed once and then lost. But that glimpse was enough to change how we see her. She's not just a moon, she's not just a companion. She's a world, scarred, painted, frozen, but real. As real as anything we've touched. And now as we drift deeper into her story, we turn to something even stranger than her surface. Something invisible, but no less important. The bond that holds her to Pluto, not just gravity, but time. Imagine never being able to look away. Not because you're forced to stare, but because your body, your bones, your very rotation is synchronized with something else. You turn, and it turns with you. You face it, and it faces you back. Forever. Not for a day, not for a year, but for billions of years. No escape, no variance. Just the same view, the same gaze, the same silent companionship across the void. This is what it means to be tidally locked. And Pluto and Charon are locked not just one way, but both ways. Mutually. Completely. In a bond so deep that even time itself cannot break it. Tidal locking is common in the solar system. Our moon is tidally locked to Earth, which is why we always see the same side, the familiar face with its dark Maria and bright highlands. The far side, often incorrectly called the dark side, remains hidden from our view, not because it's always dark, but because it never faces us. The moon rotates once every 27.3 days, and it also orbits Earth once every 27.3 days. The two rhythms are synchronized, locked. But here's the key difference. Earth is not locked to the moon. We rotate freely once every 24 hours, spinning through day and night, while the moon drifts across our sky. From the moon's surface, Earth rises and sets every 27.3 days. You could watch it arc across the horizon, watch it disappear, watch it return. The moon watches us. But we don't watch back, not in the same way. Pluto and Charon are different. They're both locked. Pluto rotates once every 6.387 days. Charon orbits Pluto once every 6.387 days. Charon rotates once every 6.387 days. Everything is synchronized. From Pluto's surface, Charon hangs motionless in the sky. From Charon's surface, Pluto does the same. Neither one moves. Neither one rises or sets. They're frozen in each other's view forever. And that raises a question. How does this happen? How do two worlds become so perfectly synchronized that even their rotation matches their orbit? The answer is tidal forces. Not the tides we think of, ocean waves rising and falling on a beach, but something deeper. A stretching, a pull, a slow, patient friction that drags on rotation until it stops. Let's start with the basics. Gravity is not uniform. When one object orbits another, the side of the object facing the partner experiences stronger gravity than the side facing away. This is because gravity weakens with distance, and the near side is closer than the far side. The difference is small, but it's enough to create a stretching effect, a tidal bulge. On Earth, this tidal bulge is most visible in our oceans. The moon's gravity pulls on the water facing it, creating a high tide. At the same time, the water on the opposite side of Earth, farthest from the moon, experiences less gravity, so it bulges outward as well. Two bulges, two high tides. And as Earth rotates beneath these bulges, the water sloshes back and forth, creating the rise and fall of the tides we see at the beach. But tidal forces don't just affect water. They affect solid material too. Rock, ice, metal. Everything stretches under tidal forces. The stretch is tiny, often just inches or centimeters, but it's real. And when a rotating object is stretched by tidal forces, something interesting happens. Imagine Earth is rotating faster than the moon orbits, which it is. The tidal bulge tries to stay aligned with the moon, but Earth's rotation drags it forward. The bulge moves ahead of the moon, and the moon's gravity pulls back on it, trying to realign it. This creates friction. Energy is lost as heat, and that friction acts like a brake, gradually slowing Earth's rotation. Over millions of years, this process slows Earth's rotation until the planet rotates at the same rate it orbits the moon. At that point, the tidal bulge stops moving. It stays aligned with the moon. The friction disappears. The planet is tidally locked. This is what happened to our moon. Early in its history, the moon was probably rotating much faster, completing a day in just a few hours. But Earth's tidal forces slowed it down bit by bit until the moon's rotation matched its orbit. Now the moon is locked, always showing Earth the same face. But Earth is much more massive than the moon, 81 times more massive, so the moon's tidal forces on Earth are weaker. Earth is slowing down too, but much more slowly. Right now, Earth's day is getting longer by about 2 milliseconds per century. In about 50 billion years long, after the sun has died, Earth will finally become tidally locked to the moon. Both will face each other, motionless forever. But that's in the future. Right now, Earth is still spinning freely, and the moon is the only one locked. Pluto and Charon are different because they are more evenly matched. Charon is 11.6% the mass of Pluto, which means her tidal forces on Pluto are much stronger than the moon's forces on Earth. Strong enough that Charon didn't just lock herself to Pluto, she locked Pluto to her as well. Scientists estimate this locking process took between 10 and 100 million years. That sounds like a long time, but in cosmic terms, it's rapid. For comparison, it took Earth's moon about 100 million years to lock to Earth, and Earth is still unlocked after 4.5 billion years. Pluto and Charon locked quickly because they were close, because Charon was large, and because the tidal forces between them were immense. And once they locked, they stayed locked. For over 4 billion years, Pluto and Charon have been frozen in this configuration, facing each other, watching each other, bound by gravity and time. But mutual tidal locking has consequences, strange subtle consequences that shape how the system behaves. First, it affects the orbit. When two bodies are tidally locked, their orbit becomes more circular over time. Any eccentricity, any elongation, any wobble gets smoothed out by tidal forces. That's why Charon's orbit is so nearly circular with an eccentricity of just 0.00002. For comparison, our moon's orbit has an eccentricity of 0.0549 over 200 times more elongated. Charon's orbit is one of the most circular in the solar system. Second, it affects the rotation axis. Tidally locked systems tend to have their rotation axes aligned with their orbital plane. Pluto's rotational axis is tilted 122 degrees relative to its orbital plane around the Sun, which means Pluto is essentially rotating on its side, like Uranus. But relative to Charon, Pluto's axis is perfectly aligned. The system rotates together as a unit, with no wobble, no precession, no drift. Third, it affects the energy. Tidal locking dissipates rotational energy as heat. When Pluto and Charon were locking the friction inside, both worlds generated enormous amounts of heat, enough to keep Charon's interior partially molten for millions of years, enough to drive geological activity, enough to create the canyons and cracks we see on her surface today. Once the locking was complete, the heat generation stopped. The system became stable, cold, quiet. And fourth, it creates a unique phenomenon, hemispheric isolation. Because Pluto and Charon always face each other, half of Pluto never sees Charon, and half of Charon never sees Pluto. If you stood on the Charon-facing hemisphere of Pluto, Charon would dominate your sky, hanging motionless overhead, huge and gray and silent. But if you walked to the opposite side of Pluto, Charon would disappear. You'd never see her. She'd be hidden beyond the horizon permanently forever. You could spend your entire life on that side of Pluto and never know Charon existed. The same is true from Charon. Half her surface sees Pluto, half doesn't. And because both worlds are locked, the dividing line never moves. It's fixed permanent, carved into geography. This creates strange asymmetries. The Pluto-facing side of Charon receives light reflected from Pluto. Not much because Pluto is dim, but enough to make a difference. The Pluto-facing side also receives more of Pluto's escaping atmosphere, which is why Mordor macula, the reddish stain at Charon's North Pole, is oriented toward Pluto. The non-Pluto-facing side receives none of that. It's darker, colder, more isolated. Scientists call this phenomenon synchronous rotation asymmetry. And it's rare. Most tidally locked moons orbit planets that aren't locked back, so the entire moon experiences varying conditions as the planet rotates. But Charon's non-Pluto-facing hemisphere never sees Pluto, ever. It's the loneliest place in the Pluto system, a hemisphere that exists in permanent ignorance of the world it orbits. Have you ever thought about what it would feel like to live on a tidally locked world? Not just intellectually, but emotionally. On Earth, we're used to change. The sun rises and sets. The moon waxes and wanes. Seasons shift. The sky is always moving, always different. But on Charon, nothing moves. Pluto is always there, or never there, depending on where you stand. The stars rotate slowly overhead, taking 6,387 days to complete one full circle. But that's the only motion. Everything else is frozen. Would it feel peaceful or suffocating? Would the constancy be comforting, or would it drive you mad? Would you long to see Pluto move just once, just to prove that time is still passing? We can't know. But the question touches something deep about how we experience the universe. We assume that orbits are dynamic, that things move, that nothing stays still. But for Pluto and Charon, motion has stopped. They've reached a state of perfect equilibrium, where every force is balanced, where nothing can change unless something external intervenes. And here's the strange part, that equilibrium might not last forever. Tidal locking is stable, yes, but not immutable. Over billions of years, even tidally locked systems can drift. The mechanism is subtle. When two bodies are locked, tidal forces don't disappear completely. They just become very small. But small forces acting over long time scales can still have effects. Tidal forces can cause the orbit to expand, pushing the moon farther from the planet. Our moon is drifting away from Earth at a rate of about 1.5 inches per year. In a few billion years, the moon will be so far away that its apparent size in the sky will be smaller than the sun's, and total solar eclipses will no longer occur. Is Charon drifting away from Pluto? Scientists aren't sure. The rate of drift, if it exists, would be incredibly slow, perhaps millimeters per year or even less. Current measurements aren't precise enough to detect it, but theoretically, it should be happening. Over tens of billions of years, Charon might drift far enough that the tidal lock breaks and both worlds start rotating freely again. But that's so far in the future, it might as well be never. The sun will become a red giant long before then, expanding to engulf the inner planets, possibly even reaching out to Neptune's orbit. Pluto and Charon might survive drifting through a solar system, transformed beyond recognition. Or they might be ejected entirely, flung into interstellar space by a close encounter with another star. Either way, the Pluto-Charon system as we know it today, locked, stable, unchanging, will not last forever. But for now, in this moment, in this epoch, they are perfect. Two worlds bound by forces they cannot control, facing each other across a distance they can never close. Not prisoners, not captives. Just partners holding on, refusing to let go. And perhaps that's the real meaning of tidal locking. Not imprisonment, but commitment. A bond so deep that it reshapes the very fabric of time and motion. A promise kept not through will, but through physics. A love, if we can call it that, written not in words, but in gravity. There are other tidally locked systems in the solar system, dozens of them. Jupiter's 4 large moons, Io, Europa, Ganymede, Callisto, are all locked to Jupiter. Saturn's moon, Titan, is locked to Saturn. Neptune's moon, Triton, will probably lock to Neptune eventually. But none of them are mutually locked. None of them face their planets the way Pluto and Charon face each other. Only Pluto and Charon share that distinction. Only they have achieved the perfect synchrony. The mutual gaze, the bond that goes both ways. And in a universe that is vast, chaotic, and mostly empty, that matters. Because it reminds us that connection is possible. That even in the coldest, darkest, most isolated corners of space, two things can find each other, hold each other, and never let go. But connection, however deep, is not the end of the story. Because Charon was not always this silent. She was not always this still. There was a time early in her history when she had something most moons never have. Something fragile, something fleeting, something that defined her for a brief moment before it vanished forever. Some things are too small to hold on to. Not because they don't matter, but because gravity has limits. Because escape is always possible if you're light enough, fast enough, desperate enough. And sometimes, what leaves never comes back. Charon may have once had an atmosphere, a thin veil of gas clinging to her surface, whispering through her canyons, pooling in her craters. And then, over millions of years, it simply left. Molecule by molecule, it drifted into space, pulled away by the sun, by cosmic rays, by the simple fact that Charon was too small to hold it. And now, she's silent, airless. A world that breathes no longer. An atmosphere is a fragile thing. We think of it as permanent. After all, Earth has had one for billions of years. But that's only because Earth is large enough, massive enough to hold it. Gravity is what keeps an atmosphere in place, pulling gas molecules down toward the surface, preventing them from floating away into space. But gravity is proportional to mass. The more massive a world is, the stronger its gravity, and the easier it is to hold on to an atmosphere. Earth has strong gravity. Our atmosphere is thick, stable, rich with nitrogen and oxygen. Molecules in the upper atmosphere move fast, thousands of miles per hour, but not fast enough to escape. Earth's escape velocity is about 7 miles per second, or roughly 25,000 miles per hour. Only the very fastest molecules hit by just the right amount of energy can reach that speed and break free. Most don't. Most stay. Most fall back down. But Charon is different. She's much smaller than Earth. Her diameter is just 750 miles compared to Earth's 7,918 miles. Her mass is about 0.025% of Earth's mass. And because of that, her gravity is weak, very weak. Charon's escape velocity is only about 370 miles per hour. That's slower than the speed of sound on Earth. It's slower than a commercial airplane. It's slow enough that even relatively light molecules like methane, nitrogen, or water vapor can reach escape velocity and drift away. And that's exactly what happened. Scientists believe that early in her history, Charon may have had a thin atmosphere made of methane and nitrogen, probably released from her interior during the period when she was still geologically active, when her subsurface ocean was freezing and cracking her crust. Volcanic vents, or more accurately cryovolcanic vents, may have released gases trapped in the ice, allowing them to rise to the surface and form a temporary atmosphere. But temporary is the key word, because Chiron's gravity was too weak to hold on to those gases. Over time, they escaped, not all at once, but slowly, steadily, molecule by molecule, until nothing was left. This process is called atmospheric escape, and it's one of the most important factors in determining whether a world can support an atmosphere, and by extension, whether it can support life. There are several mechanisms by which atmospheres escape, and each one tells a different story about the world it's leaving behind. The first mechanism is thermal escape, also called Jeans escape. It works like this: gas molecules in an atmosphere are always moving, bouncing off each other, vibrating with energy. The hotter the atmosphere, the faster they move. Temperature is just a measure of molecular motion. Heat is speed. And if a molecule is moving fast enough, and it's in the upper atmosphere, where there are fewer other molecules to collide with, it can reach escape velocity and leave the planet entirely. On Earth, this happens mostly with hydrogen and helium, the lightest elements, because they move faster than heavier molecules at the same temperature. That's why Earth has almost no hydrogen or helium in its atmosphere. They've mostly escaped over the past 4.5 billion years. Heavier molecules like nitrogen and oxygen move too slowly to escape, so they stay. But on Charon, even heavier molecules like methane can escape because Charon's escape velocity is so low. Methane molecules at Charon's surface temperature around minus 380 degrees Fahrenheit don't move very fast. But in the upper atmosphere where sunlight can heat them slightly, some molecules move fast enough to reach escape velocity. And once they do, they're gone. The second mechanism is photochemical escape. This happens when ultraviolet light from the sun hits molecules in the upper atmosphere and breaks them apart. For example, UV light can split methane molecules into smaller fragments, hydrogen atoms, and hydrocarbon radicals. The hydrogen atoms are very light, so they escape easily. The hydrocarbon fragments might fall back to the surface, or they might react with other molecules to form more complex compounds, like the tholins we see at Charon's North Pole. The third mechanism is solar wind stripping. The solar wind is a stream of charged particles, mostly protons and electrons, constantly flowing from the sun. When it hits an atmosphere, it can strip away molecules, especially if the planet doesn't have a strong magnetic field to deflect the wind. Earth has a magnetic field, so we're protected. Mars doesn't, which is why Mars lost most of its atmosphere over billions of years. Charon has no magnetic field, so any atmosphere she had would have been vulnerable to solar wind stripping. And the fourth mechanism is impact erosion. When a large asteroid or comet hits a planet, the impact can blast part of the atmosphere into space. This is especially effective on small worlds like Charon, where the escape velocity is low and the impact's relatively large. A single major impact might have stripped away a significant fraction of Charon's atmosphere all at once. All four of these mechanisms probably played a role in Charon's atmospheric loss. But the most important one was simply thermal escape, because Charon's gravity is so weak. Even if she had released a thick atmosphere early in her history, it wouldn't have lasted. The molecules would have drifted away slowly, but inevitably until nothing remained. How do we know Charon had an atmosphere if it's gone now? We don't, not for certain, but there are clues. The tholins at Mordor Macula suggest that methane was once present on Charon's surface, and methane can exist as a gas in the right conditions. The canyons and cracks in Charon's crust suggest that gases were released from her interior during cryovolcanic activity. And computer models of Charon's thermal evolution suggest that she was warm enough early on to outgas volatiles like nitrogen and methane, but the evidence is indirect. We have no direct measurements of an atmosphere on Charon. New Horizons flew past in 2015 and detected no atmosphere, no gas, no haze, no pressure. Charon's surface is exposed directly to space, unprotected, frozen. If she ever had an atmosphere, it's long gone. Compare this to Pluto. Pluto has an atmosphere. It's thin, the surface pressure is about 100,000 times lower than Earth's, but it's real. It's made mostly of nitrogen with traces of methane and carbon monoxide. Pluto's gravity is stronger than Charon's, about twice as strong, which helps. But even Pluto's atmosphere is escaping. Scientists estimate that Pluto loses about 500 tons of nitrogen every hour, blown away by the solar wind, evaporating from the surface, drifting into space. Why does Pluto still have an atmosphere if it's escaping? Because Pluto has a reservoir. The nitrogen isn't just in the atmosphere, it's also frozen on the surface in the vast ice plains of Sputnik Planitia. When Pluto is closer to the Sun in its elliptical orbit, the ice warms slightly and sublimates, turning directly from solid to gas, replenishing the atmosphere. When Pluto is farther from the Sun, the atmosphere freezes back onto the surface. It's a cycle constantly balancing between gas and ice. Charon doesn't have this. She has no large ice reservoir to replenish her atmosphere. Any gases she releases escape and don't come back. And so, she's silent now, airless, a world without breath. But here's what's interesting: having no atmosphere isn't necessarily a bad thing. It just means Charon is different. Without an atmosphere, Charon's surface is pristine, unweathered, unchanged by wind or rain or chemical reactions with gases. Every crater, every canyon, every feature on her surface is preserved exactly as it formed, like a photograph frozen in time. Scientists call this vacuum weathering, and it's one of the reasons why airless worlds like the Moon and Mercury are so valuable for studying the solar system's history. They're archives, records, places where the past is still visible. On Earth, erosion erases history. Wind wears down mountains. Water dissolves rock. Plants and animals burrow and build. A landscape on Earth might look completely different after just a few million years. But on Charon, a landscape can stay the same for billions of years because nothing is there to change it except the occasional impact. This makes Charon a time capsule. Her surface tells the story of the early solar system, when impacts were common, when the Kuiper Belt was crowded, when collisions shaped worlds. Every crater on Charon is a time stamp, a marker of when something hit her. By counting craters and measuring their sizes, scientists can estimate the age of different regions on Charon's surface. The heavily cratered southern hemisphere is ancient, perhaps as old as Charon herself. The smoother northern plains are younger, resurfaced by geological activity after the craters were erased. But there's a trade-off. Without an atmosphere, Charon has no weather, no clouds, no seasons, no rain. She has no protection from radiation. Cosmic rays and solar wind hit her surface, directly breaking apart, molecules altering chemistry, darkening ice. Over billions of years, this radiation damage accumulates, changing the color and composition of the surface. The dark reddish tholins at Mordor macula are partly a result of this radiation processing. Would Charon be more interesting if she still had an atmosphere? Maybe. Atmospheres create complexity. They create weather chemistry dynamics. Titan, Saturn's largest moon, has a thick atmosphere and looks nothing like Charon. Titan has clouds, rain rivers, lakes, all made of methane instead of water, but still, it's a world in motion, a world where things change. But Charon is beautiful in her stillness, in her silence, in her refusal to change. She's a monument, a memorial, a world that exists not to do anything, but simply to be. And maybe that's enough. There's something almost melancholic about atmospheric escape, isn't there? The idea that something you once had is now gone, drifted away, irretrievable. Charon's atmosphere, if it existed, is now scattered across the Kuiper Belt, dispersed into the void, mixed with the thin gas between stars. It's not destroyed matter, can't be destroyed, but it's lost. Unrecoverable. Charon will never get it back. Mars experienced the same loss. Mars once had a thick atmosphere, warm enough to support liquid water on its surface. Rivers flowed, lakes filled, maybe even oceans. But over billions of years, the atmosphere escaped, stripped away by the solar wind lost to space. Now, Mars is cold, dry, airless. The rivers are gone. The lakes are frozen. The past is buried under dust. Venus went the other way. Venus once had water, maybe even oceans, but a runaway greenhouse effect boiled it all away. The water vapor escaped into space, broken apart by UV light, and now Venus is hotter than Mercury, with a crushing atmosphere made of carbon dioxide. Different story, but the same lesson: atmospheres are fragile. They can be lost, transformed, destroyed. Nothing lasts unless gravity is strong enough to hold it. Earth is lucky. We're just the right size, with just the right gravity to hold on to an atmosphere. We're also protected by a magnetic field which deflects the solar wind and keeps our atmosphere from being stripped away. And we have a stabilizing influence, the moon, which helps regulate our axial tilt and keeps our climate relatively stable. Without those things, Earth might have gone the way of Mars or Venus, and we wouldn't be here to think about it. Charon reminds us that size matters, that mass matters, that in the cosmic lottery, some worlds win and some worlds lose, and the difference comes down to physics, not fate. Charon lost her atmosphere if she ever had one, not because she did anything wrong, but because she was too small, too light, too far from the sun to replenish what was lost. And now she drifts in the dark, silent, and still a world without voice, but not without story. Because even in her silence, even in her emptiness, Charon speaks. She tells us about limits, about loss, about what it means to be small in a universe that doesn't care. And yet, for all that she's lost, Charon is still here, still orbiting, still facing Pluto, still holding on. She didn't need an atmosphere to survive. She didn't need breath to endure. She just needed gravity, and Pluto, and time. Some things leave, some things stay. And sometimes what stays is enough. But Charon's silence, her stillness, her cold isolation, these things were not always her defining features. There was a moment brief in cosmic terms when humans reached out across the solar system and touched her. When a machine built by hands that would never see her flew past at impossible speed and saw her for what she truly was. 9 years, 3 billion miles, one chance, no room for error, no second attempt. Just a spacecraft the size of a grand piano, hurtling through the dark faster than a speeding bullet, carrying humanity's only hope of seeing Pluto and Charon up close. And when the moment came, it lasted just a few hours. A single flyby, a glimpse, and then silence. This is the story of New Horizons. Not just a mission, but a pilgrimage, a journey to the edge of everything we've explored, to a place so far that light itself takes over 4 hours to reach it. And what that mission revealed wasn't just data. It was proof that even at the farthest edges of our solar system, wonder still waits. The mission began long before the spacecraft launched. It began with a question: why hasn't anyone been to Pluto? By the early 2000s, humanity had sent probes to every planet in the solar system except Pluto. Mariner flew past Mercury. Venera landed on Venus. Viking touched Mars. Pioneer and Voyager visited Jupiter, Saturn, Uranus, Neptune. But Pluto remained untouched, unseen. A world known only through blurry images from Earth-based telescopes and the Hubble Space Telescope, which could barely separate Pluto and Charon into 2 distinct points of light. Why the delay distance? Difficulty. Cost. Pluto is farther from the Sun than any other planet, an average of 3.7 billion miles. To reach it, a spacecraft would need to travel faster than any probe before it, using a trajectory so precise that even the tiniest error would cause it to miss Pluto entirely. And because Pluto is so far, communication with the spacecraft would be slow. Radio signals traveling at the speed of light would take over 4 hours to reach Earth. That meant no real-time control, no joystick, no steering. The spacecraft would have to operate autonomously, making decisions on its own, trusting that the humans who built it had thought of everything. It was a gamble, and NASA almost didn't take it. Funding for a Pluto mission was repeatedly proposed and canceled throughout the 1990s. The mission was deemed too expensive, too risky, too uncertain. But a small group of planetary scientists refused to give up. They argued that Pluto was the last unexplored world in the classical solar system, and that if we didn't go soon, an entire generation of scientists and engineers would live and die without ever seeing it. Finally, in 2001, NASA approved the mission. It was called New Horizons, and it had one goal: fly past Pluto and Charon, take as many pictures and measurements as possible, and send the data back to Earth. No landing, no orbiting, just a flyby, moving too fast to stop capturing everything in a single pass. The spacecraft launched on January 19, 2006 from Cape Canaveral, Florida. It was the fastest object ever launched from Earth, at the time, reaching a speed of 36,000 miles per hour shortly after liftoff. To save time, the mission planners chose a trajectory that would send New Horizons past Jupiter, using the giant planet's gravity to boost the spacecraft's speed, a technique called a gravity assist. In February 2007, New Horizons flew past Jupiter at a distance of 1.4 million miles, snapping photographs of the planet's swirling storms and its volcanic moon, Io. The encounter worked perfectly. Jupiter's gravity accelerated New Horizons to over 50,000 miles per hour, shaving 3 years off the journey to Pluto. And then came the waiting. After Jupiter, there was nothing. No planets to photograph, no moons to study, just empty space. The spacecraft went into hibernation mode, shutting down most of its systems to conserve power, waking up briefly every few months to check in with Earth and run diagnostics. The team on the ground waited. Some of them got married, had children change careers. The spacecraft drifted silently through the void, covering 1 million miles every day alone in the dark. 9 years. That's how long it took. 9 years of waiting, hoping, trusting that the spacecraft would survive, that its instruments wouldn't fail, that no tiny piece of debris would puncture its hull and end the mission before it even began. Deep space is not empty. It's full of dust, ice particles, micrometeoroids, tiny fragments of rock and metal, traveling at tens of thousands of miles per hour. A collision with even a grain of sand at those speeds could be catastrophic. But New Horizons survived. And on December 6th, 2014, the spacecraft woke up for the final time. Pluto was still 162 million miles away, but the encounter phase had begun. The instruments powered on, the cameras focused. The mission that had been planned for over a decade was finally about to happen. For the next 7 months, New Horizons approached Pluto and Charon, taking pictures every few days, watching as the two worlds grew from tiny dots to disks, from disks to globes, from globes to landscapes. By June 2015, the images from New Horizons were already better than anything Hubble had ever captured. By July, they were extraordinary. Scientists on the ground saw features they had never imagined: mountains, valleys, plains, colors, textures. Pluto wasn't a dead, boring ice ball. It was a world, and so was Charon. July 14th, 2015, the day of closest approach. New Horizons flew past Pluto at a distance of 700-800 miles, moving at 3,800 miles per hour. At that speed, the entire encounter lasted just a few hours. The spacecraft had been programmed to take as many pictures as possible to measure temperatures, compositions, particle densities, magnetic fields. It couldn't transmit data during the flyby. It was too busy observing, storing everything on its internal memory. Communication would come later. For 6 hours, New Horizons was silent. The team on Earth waited, unable to do anything, unable to help, unable to know if the mission had succeeded or failed. If something went wrong, if the spacecraft hit a piece of debris, if a computer glitched, if an instrument malfunctioned, they wouldn't know until it was too late. All they could do was wait. And then, at 8:53 p.m. Eastern Time, a signal arrived, a simple message transmitted from 3 billion miles away. "I'm alive. The flyby was successful. Data is intact." The control room erupted. People cheered, cried, hugged. 9 years of work, a $1 billion mission. All of it came down to the single message. New Horizons had survived, and the data it carried would change everything. But here's the thing, getting the data back took time, a lot of time. New Horizons transmitted data at a rate of just 1 to 4 kilobits per second, depending on the distance and the alignment of its antenna. For comparison, a typical home internet connection in 2015 was about 10,000 kilobits per second, over 2,500 times faster. At New Horizons' transmission rate, it took over 4 hours just to send a single high-resolution image. The The spacecraft had collected about 50 gigabits of data during the flyby. At 1 kilobit per second, that would take over 15 months to transmit. So the team prioritized. The most important images, the ones of Pluto's heart-shaped glacier, Charon's canyons, the atmospheric haze, were sent first. The rest came later, slowly pixel by pixel spread out over more than a year. The final data from the Pluto flyby didn't arrive until October 2016, over 15 months after the encounter. Think about that. In an age where we expect instant results, where we can stream high-definition video from across the planet in seconds, New Horizons reminded us that space is different. Space is patient. Space is slow. You can't rush a signal that's traveling 3 billion miles. You can't speed up light. You just have to wait. And the waiting was worth it, because the images that came back were stunning. Pluto's heart officially named Tombaugh Regio, after Clyde Tombaugh, the astronomer who discovered Pluto in 1930, turned out to be a vast plain of nitrogen ice, over 600 miles wide, smooth and bright, and geologically young. No craters, no scars. Just pure fresh ice, suggesting that Pluto's surface is still active, still renewing itself, possibly through cryovolcanism or slow convection currents in the ice. And Charon was just as surprising. Her canyons, her mountain, her dark red pole, all of it visible in sharp detail for the first time. Scientists saw things they didn't expect, couldn't explain, had to rewrite their theories to accommodate. Charon wasn't dead. She was a monument, an archive, a world that had lived, changed, and then frozen, preserving her history in ice. But New Horizons didn't stop at Pluto. After the flyby, the spacecraft kept going deeper into the Kuiper Belt toward another object. A small reddish snowman-shaped rock, officially named Arrokoth. On January 1st, 2019, New Horizons flew past Arrokoth, making it the most distant object ever visited by a spacecraft. The encounter was brief, the data limited, but it added another piece to the puzzle of how the solar system formed. And now, New Horizons is still flying, still moving, still transmitting. It's about 5 billion miles from Earth, traveling at 32,000 miles per hour, heading toward the edge of the solar system. Its power supply, a radioisotope thermoelectric generator, fueled by plutonium-238, will last until the 2030s. After that, the spacecraft will go silent, drifting through interstellar space for billions of years, carrying a message from Earth in case anything ever finds it. But here's what most people don't realize: New Horizons was almost canceled, multiple times. In the early 2000s, funding was uncertain. In 2003, a key instrument failed during testing and had to be rebuilt. In 2005, budget cuts threatened to delay the launch, which would have missed the optimal launch window and forced the mission to wait another decade. Even during the flight, there were close calls. A software glitch in 2015, just days before the Pluto flyby, put the spacecraft into safe mode, and the team had to work around the clock to restore it in time. Every exploration mission is fragile. Every mission teeters on the edge of failure, held together by engineering luck and the stubborn refusal of a few people to give up. New Horizons succeeded not because it was easy, but because a small group of scientists and engineers believed it was worth the risk. And they were right. Because what New Horizons gave us wasn't just data. It was perspective. A reminder that the universe is vast and we are small, but we are curious. And that curiosity can carry us farther than we ever imagined. Pluto and Charon are no longer abstract. They're places. Real places. Places we've seen, measured, understood, if only for a moment. There's a lesson in that. A lesson about patience, about perseverance, about the willingness to wait 9 years for 3 hours of data, 16 months for a full picture, a lifetime for a single answer. Science is not instant. Discovery is not easy. But it's worth it, every time. And so, New Horizons flies on alone in the dark, carrying the dreams of everyone who built it, everyone who waited for it, everyone who will never see Pluto. but knows that someone did. That something we made touched the edge of the unknown and came back to tell us what it found. But the story doesn't end with the flyby. Because what New Horizons revealed, what those images, those measurements, those glimpses of ice and shadow showed us, is that even the smallest, coldest, most forgotten worlds in the solar system have something to teach us. About beauty, about time, about the quiet persistence of things that refuse to disappear. We've traveled far tonight. Across billions of miles, across billions of years. From the moment Charon was born in violence to the moment she was finally seen, we've followed her through darkness, through silence, through a story that almost no one knows. And now, as we drift toward the end, there's one question left. One question that matters more than all the science, all the data, all the measurements. Why does Charon matter? Why should we care about a frozen moon at the edge of the solar system? A world so far that sunlight barely reaches it. A place no human will ever visit, no life will ever touch. The answer is not simple, but maybe it doesn't need to be. Charon matters because she reminds us that even in the darkest, coldest, loneliest corners of the universe, there is beauty. Not the kind of beauty we're used to, not sunsets or oceans or forests, but a different kind. The beauty of persistence, of partnership, of things that refuse to disappear simply because no one is watching. For 4.6 billion years, Charon has been there, orbiting Pluto, facing him, holding him. She has witnessed the entire history of the solar system from a front row seat at its edge. She saw the planets form, saw the dinosaurs rise and fall on Earth, saw the first humans look up at the stars and wonder what lay beyond. And through it all, she remained, silent, patient, unchanging. And that constancy is rare. Most things in the universe are temporary. Stars burn out, planets collide, galaxies drift apart. Even the atoms in our bodies will one day decay. Their particles scattered across space, recycled into new stars, new worlds, new forms we can't imagine. Nothing lasts forever. Nothing except perhaps the bond between Pluto and Charon. Scientists estimate that their mutual tidal lock will persist for trillions of years, long after the sun has died, long after the Milky Way has merged with Andromeda, long after the universe itself has cooled into darkness. Pluto and Charon will still be there, spinning together, facing each other, locked in a dance that began before Earth had oceans, and will continue long after the last star has faded. That's not just science, that's poetry. A reminder that some things endure not because they're strong, but because they're bound together by something deeper than strength. Gravity, time, a collision that should have destroyed them, but instead made them inseparable. And maybe that's the real lesson of Charon. That connection is possible even in a void. That partnership can exist even in the cold. That two things born from violence can hold each other through billions of years and never let go. We see this pattern throughout the solar system. Earth and the moon born from a collision bound together ever since. Binary stars orbiting each other, sharing mass dying together in supernova explosions. Even black holes, the most destructive forces in the universe, can orbit each other, spiraling inward over millions of years, until they merge in a burst of gravitational waves. The universe, for all its chaos, has a way of creating partnerships, of pulling things together instead of tearing them apart. And Charon is one of the most beautiful examples of that principle, not because she's spectacular, not because she's active or alive, but because she's loyal. She's stayed, she's held on, she's refused to drift away into the dark. But Charon also reminds us of our own limits, because for all our technology, for all our ambition, we've only seen her once. New Horizons flew past in 2015, captured a few thousand images, and then kept going, never to return. No other mission to Pluto or Charon is planned. Not in this decade, not in the next, maybe not in our lifetimes. And that means everything we know about Charon comes from a single encounter, a few hours of observation, a glimpse frozen in time. We don't know if her interior is still warm, if liquid water exists beneath her crust, if her geology is truly dead or just sleeping. We don't know how old Mordor Macula really is, or whether her canyons are still shifting, or what her craters look like up close. We don't know because we haven't gone back, and we probably never will. There's something bittersweet about that, isn't there? The idea that we saw her once and now she's gone, fading back into obscurity, a memory preserved in data, but no longer accessible. It's like meeting someone remarkable, someone who changes how you see the world, and then watching them walk away, knowing you'll never see them again. But maybe that's okay. Maybe Charon doesn't need us to come back. She was there long before we arrived, and she'll be there long after we're gone. She doesn't need validation. She doesn't need attention. She just needs Pluto, and Pluto needs her, and that's enough. Still, there's a part of me, maybe a part of all of us, that wishes we could return, that wishes we could land on her surface, walk through Serenity Chasma, stand at the base of Kubrick Mons, and look up at Pluto, hanging motionless in the sky. That wishes we could touch her ice sample, her craters drill into her crust, and see what lies beneath. But even if we never do, even if Charon remains forever out of reach, we know she's there, and we know her story, and that matters. Because stories are how we connect to things beyond ourselves. Stories are how we make meaning from data, how we turn measurements into wonder, how we take a frozen moon billions of miles away and make it feel real. And Charon's story is one worth remembering, a story of collision and creation, of loss and loyalty, of a moon that was almost invisible, almost forgotten, but turned out to be one of the most unique objects in the solar system. A moon that taught us about tidal locking, about atmospheric escape, about the limits of gravity and the endurance of ice. A moon that reminded us that size doesn't determine significance, that even the smallest worlds can carry the deepest mysteries. So, what do we take from all of this? What do we carry with us as we drift back from Charon, back across the solar system, back to Earth? Maybe that the universe is full of places we'll never visit, wonders we'll never see, stories we'll never fully understand. And that's okay. Because the act of reaching out, of trying to see, of asking questions, even when the answers are impossibly far away, that act is what makes us human. That curiosity, that refusal to accept ignorance, that insistence on looking into the dark and trying to find meaning, that's what exploration is. That's what science is. Charon doesn't care if we see her. She doesn't care if we understand her. She just exists quietly, patiently holding Pluto in the dark. But we care. We looked. We traveled 3 billion miles to see her. We built a machine, launched it into the void, waited 9 years, and captured her face in a few precious hours of light. And because we did that, Charon is no longer just a moon. She's a place, a world, a story. And stories once told never truly end. They echo, they linger, they change how we see everything else. So, here's to Charon, the forgotten moon, the dark companion, the twin who never left, the world born from violence shaped by time, painted by Pluto's breath, and locked in a dance that will outlast stars. She's still there even now, as you listen to this, spinning slowly, facing Pluto, unchanged. And maybe if you ever look up at the night sky and think about the edge of the solar system, about the cold and the dark and the places we've barely touched, you'll remember her. Not as data, not as a photograph, but as a reminder that even in the darkest places, something beautiful can exist, something permanent, something that refuses to be forgotten simply because it was never meant to shine. Some things don't need light to matter, they just need to be, and Charon is. Quiet, cold, and patient, forever. Thank you for drifting with me through this quiet journey, for letting the story of Charon unfold softly, without rush, without noise. If you found peace in this exploration, If these distant worlds brought you a moment of calm, I hope you'll stay for the next one. Because the universe is vast, and there are so many more stories waiting in the silence. Stories of forgotten worlds, of ancient light, of mysteries that sleep in the dark. Until then, rest well, dream gently, and remember, even at the edge of everything, we are not alone. Good night.